This video describes the research and development of a drone-based AI-powered real-time freeway incident detection system. The project was sponsored by the National Institute for Congestion Reduction, a United States Department of Transportation National University Transportation Center, with additional support from the Florida Department of Transportation. The University of South Florida research team has complementary expertise that ensured the success of this project. On the far left is Dr. Pei-Sung Lin, who contributed to project development. Dr. Achilles Cortelis, the co-principal investigator of this project and one of our drone operators, oversaw drone procurement, compliance, and maintenance, as well as experiment design, data collection, and reporting to National Institute for Congestion Reduction. Mr. Joseph Post, an aviation expert, assisted with airspace analysis and participated in field experiments. Dr. Yu Zhang, the principal investigator, led the project development and management, coordinated with the United States Department of Transportation and the Florida Department of Transportation, and supervised the team's work. Mr. Brian Porter is a Florida Department of Transportation District 7 employee, a master's student, and another drone operator for the team. Brian was actively involved in collecting data, coordinating with Sun Guide and Road Ranger to gather real-time information at crash sites. Dr. Biley was responsible for developing the learning-based algorithm and detection platform and integrating system hardware and software. Additionally, he has played a crucial role in conducting field experiments and video data collection. Lastly, Mr. Madi Monemanadahai was primarily responsible for training the learning-based model. In addition to the current research members, we would like to thank the former students who contributed to the project. Dr. Hualong Tang played a crucial role in deploying and debugging the You Only Look Once model used in this project. Ms. Kirthana Yelchuri dedicated considerable time to labeling the collected images, which was vital for developing the learning model. We also extend our thanks to the Florida Department of Transportation District 7 Traffic Operations Office, the Regional Transportation Management Center, and the Road Ranger program for allowing Mr. Porter to accompany the Road Rangers and collect data during the project's early stages. Additionally, we acknowledge the Florida 511 website of the Florida Department of Transportation's Regional Transportation Management Center for providing real-time traffic information, which was utilized throughout this project. Furthermore, we recognize the early-stage collaboration of Drs. Benjamin Colucci, Alberto Figueroa Medina, and Yvette Cruzado from the University of Puerto Rico at Mayagüez as part of the NICR 4-3 project. Our presentation will cover four main aspects: background and project introduction, system hardware and software development, field validation, and conclusions. The Federal Highway Administration's Office of Operations identified traffic incidents as the primary source of non-recurrent congestion. Traffic incidents disturb traffic flow, cause cascading congestion upstream, and can even affect opposite direction traffic. The impact of severe crashes could propagate to other parts of the roadway network. Incidents can also trigger secondary crashes and further deteriorate traffic conditions. The process of incident clearance can take hours, and the dissipation of negative impacts may take even longer. Therefore, effective traffic incident management is crucial. Rapid detection and timely clearance of incidents are essential to alleviate congestion and reduce its propagation effects. Currently, traffic incident detection relies on reports from individuals involved in the crash and bystanders who drive by. Proactive methods employed by public agencies include highway patrol and road rangers who patrol and report any incidents they encounter. In addition, traffic management centers use CCTV systems to detect crashes. However, these detection methods have several limitations. Human patrols are dependent on manpower availability and thus have limited coverage, resulting in response delays. Some patrol areas also have limited operational hours and are not available 24/7. CCTV systems have a limited field of view. Excessive field of view affects image quality and can impair incident detection performance. Visual cameras are also dependent on lighting and weather conditions, require maintenance, and are susceptible to vandalism. Additionally, a high density of CCTV cameras can lead to data overload when all the data needs to be transmitted back to the traffic management center. With the advancement of drone technologies and the availability of high-resolution cameras, both visual and thermal, we can now leverage these tools effectively. Thermal cameras help address privacy concerns and provide robust performance, particularly in low visibility and nighttime conditions. Drones can bridge the gaps in existing CCTV systems by covering blind spots, especially in areas with complex road geometry. They can adapt to various needs, offering a dynamic surveillance solution. Additionally, drones can monitor vehicle detours, providing insights into the overall system's functionality and cost-effectiveness. Our research goal is to develop a drone-based, AI-powered, real-time freeway incident detection system to enhance incident management. To achieve this goal, we have outlined 3 specific objectives. 1. Develop an effective learning algorithm to ensure real-time detection with high accuracy and efficiency. 2. Develop the necessary software and integrate the hardware components. This project goes beyond pure academic research. We aim to create a practical tool for professional use. 3. Test and validate the developed system to ensure its operability and efficiency before transferring the technology to relevant agencies. Here is our research approach. As mentioned earlier, the first step is to collect extensive data. Mr. Post assisted us in conducting an airspace analysis to ensure we did not interfere with any controlled airspace and were compliant with Federal Aviation Administration's requirements. We designed experiments to collect data at various times of the day and from different freeway locations. After collecting the data, we generated vehicle trajectory images to use as input for our learning model. Ours is a classification model. We implemented techniques to improve its computational efficiency, ensuring that 2-minute videos could be processed in under 1 minute 20 seconds. This allows for continuous video transmission to our workstation for quick processing, enabling real-time detection. Additionally, we developed a smartphone app for transmitting the drone's position and thermal imagery from the drone's remote controller. We also created a web-based graphical user interface, with the learning algorithm running in the background, for incident detection and alerting. This interface allows operators on the ground, whether on-site, at the Transportation Management Center, or on campus, to monitor real-time incidents and control the detection process remotely, even if the drones become fully autonomous in the future. The final step was field validation. We selected an appropriate site, prepared and flew the mission, and validated our system's accuracy and efficiency. Next, we will delve into the development of our drone-based, AI-powered, real-time freeway incident detection system. The figure on the left illustrates the hardware architecture of our system. The live deck functions as a secondary remote controller, primarily responsible for decoupling data transmission from flight control operations. This enhances data transmission efficiency while ensuring flight safety. Similar to the remote controller, the live deck facilitates two-way data communication with the drone via 2.4 GHz wireless signals, providing real-time access to the drone's flight status and thermal camera video. The figure on the right showcases the hardware setup during freeway incident detection missions. At the center is the drone equipped with a thermal camera. On the left is the live deck connected to a smart device running the data transmission app we developed. On the right is the remote controller paired with a smart device running the drone manufacturer's control app, used by the pilot to control the drone. To control the drone's position data and imagery transmission from the live deck, we developed a control application for smart devices. This app receives real-time thermal camera video and drone GPS coordinates from the live deck and transmits this information to the video streaming platform and workstation. The figures on the right display the main interface and the start/stop transmission page of the application. As shown, when the operator clicks on the NICR live push button to enter the information transmission page, the drone's thermal camera footage appears at the center of the screen. Two buttons on the left side control the start and stop of the information transmission. Notifications are displayed in the middle of the page at the start and stop of the transmission, to keep the operator informed of the current status. Here is the software architecture of the system, detailing each software module on both the drone side and the workstation side. The figure on the left illustrates each software module for the drone. Once the detection mission is initiated, the smart device connected to the live deck starts the real-time transmission thread for the drone's GPS coordinates and the live video streaming thread for the thermal camera, broadcasting this data to the workstation. The figure on the right depicts each software module on the workstation, which is responsible for data processing. Upon starting the detection mission, the workstation activates the GPS coordinate receiving thread and the thermal video live recording thread. It also simultaneously starts the processing thread for the recorded video to detect traffic incidents in real time. The software flowcharts for the drone and workstation threads are presented here. The flowchart on the left illustrates the software process on the drone side. When Freeway incident detection begins, the Android-based software first activates the drone GPS coordinate transmission thread, followed by the thermal camera live video streaming thread. While these two threads are running, the software also receives control commands from the operator in real time and stops both threads when it receives a command to stop detection. The flowchart on the right shows the software process on the workstation side. After starting the detection mission, the software first opens the drone GPS coordinate receiving thread to obtain real-time GPS data from the drone. Then, it activates a live video recording thread to record the thermal camera footage transmitted in real time from the drone. Additionally, the software runs an AI-based Freeway incident detection algorithm on the recorded 2-minute-long video to achieve real-time incident detection. While these three threads are operating, the software also receives control commands from the operator in real time and stops all three threads simultaneously when a stop command is received. It is worth emphasizing that the live video recording thread on the workstation side starts a 2-minute-long recording subthread every 40 seconds. This approach leverages the parallel processing capability of the GPU on the workstation to maximize coverage of the observed road sections, thereby reducing the probability of false detections. To enable operators to control the entire system from various devices and check real-time results, we developed web-based control software. This slide shows the detection control page of the software during a detection mission. The interface includes highway information and detection-related parameters, mission control buttons, detection status with a text version of real-time results, real-time footage from the drone's thermal camera, and visualized detection results. The detection status box displays the running threads, with a verification dot for each process turning green when active. Real-time detection results are shown in text format, with items indicating traffic incidents highlighted in red. The lower half of the interface features the drone's thermal camera footage and visualized detection results in real time, allowing the operator to easily pinpoint the exact location of a traffic incident on a map. To enhance user-friendly operation, this detection system is also adapted for smaller screens on smart devices such as tablets and smartphones. Here, the interface of the control software is shown on a smartphone screen. During the field validation experiment, we successfully detected a traffic accident on April 18, 2024, and captured the resulting traffic congestion. The location chosen for our validation experiment was a segment of Interstate 75, before exit 279. This segment was selected due to its typical significant traffic congestion between 4:30 and 6 p.m. on weekdays and the increased risk of rear-end crashes. The red box in the figure marks the specific detection segment of the highway, while the yellow arrow indicates the drone's flight direction. We conducted the validation experiment between 4:30 and 5:30 p.m. to test the system's effectiveness. During the experiment, the drone flew at 200 feet above ground level and cruised at 10 miles per hour. Next, we will show the situation at the verification experiment site. We quickly connected the remote controller to the smartphone running the drone's official ground control app and installed the drone's battery to complete the drone's deployment and prepare it for takeoff. In parallel with the deployment of the drone, we also synchronized the launch of the data transmission app on the smartphone connected to the live deck in order to transmit the drone's thermal camera footage and GPS coordinates in real time to the workstation side. When the data had successfully commenced transfer, the corresponding parameter changes were displayed on the screen. Once the above preparations were completed, the drone successfully took off under the pilot's supervision and carried out the corresponding traffic incident detection mission according to preset waypoints. During the detection process, the pilot can control the drone and monitor the thermal camera footage along with the drone's flight status to ensure flight safety. Meanwhile, during the drone detection flight, the ground operator can observe the system detection status, the drone's thermal camera footage and detection results of processed videos at any time through our design detection control software. In addition, the operator can also pause, resume and stop the detection system at any time by clicking on control buttons on the web page. When the drone's flight is stopped, the operator can click the Stop Detection button on the control software to stop the related detection threads on the workstation. Once the detection mission is completed, the drone will land to perform operations such as changing batteries. For completed detection missions, the operator can review at any time via the history review function of the detection control software for subsequent analysis and other operations. In addition, the operator can click on any dot on the visualization map to view the thermal video corresponding to the dot, thus understanding the type and severity of the traffic incident and its impact on traffic. Based on the history review function of our detection control software, we extracted the visualization results of the 3 detection experiments and performed the related analysis. According to the previous description, there was no traffic rear-end accident during the first detection flight. The first figure on the left shows some recurrent traffic congestion near the highway exit, mainly due to peak hour traffic, with more vehicles exiting the highway and being blocked by traffic signals after the off-ramp. The second detection flight was conducted after the rear-end traffic accident had occurred. The results showed that the crash caused non-recurrent traffic congestion upstream, while downstream congestion had disappeared due to lane blockage at the crash site. According to the text version of the monitoring results on our detection control webpage, our detection system identified the crash at 5:02 p.m. The results of the third detection flight further demonstrated the upstream propagation of the non-recurrent traffic congestion caused by the accident. At this point, all detection points upstream of the crash site are marked in red, indicating a state of traffic congestion. From the history review page of the web-based detection control software, we can also obtain recorded videos and video screenshots from the drone's thermal camera at the incident time. On the left, during the first flight that started at 4:48 p.m., the traffic crash had not yet occurred. During the second flight, which began at 4:59 p.m., the drone had already captured the crash. The vehicles involved in the crash are visible, along with a significant increase in traffic density. When the alert appears on the graphical user interface, the ground operator can click on the specific spot and view the recorded video. This allows the operator to obtain detailed information about the crash, such as the number of vehicles involved, the affected lane, and the overall traffic situation at the time. This feature provides a powerful and efficient verification tool. Additionally, we obtained information about the crash from the Florida 511 website. According to Florida 511, a two-vehicle rear-end crash occurred just before exit 279, on Interstate 75, on April 18, 2024, at approximately 5:09 p.m. This incident was possibly caused by existing traffic congestion on the off-ramp, leading to the rear-end collision. CCTV video from the website revealed that a red sedan rear-ended an SUV in the outside lane. Additionally, according to the Regional Integrated Transportation Information System, the crash caused vehicle congestion for more than 5 miles upstream, with the congestion persisting until approximately 7 p.m. Here is a snapshot from the Regional Integrated Transportation Information System. It shows that the crash was reported to the Florida Highway Patrol around 5:09 p.m. According to the information in the system, the crash was verified by the Florida Department of Transportation around 5:15 p.m. However, our drone-based traffic accident detection system detected the accident at 5:02 p.m. and saved the video of the scene for timely verification by the Transportation Management Center. This demonstrates the timeliness and convenience of our system in detecting traffic crashes. Next, we will summarize our findings. In summary, we have developed a drone-based, AI-powered, real-time incident detection system. Drones provide flexibility and robustness compared to pole-mounted visual cameras of CCTV systems. The neural network-based learning aspect ensures that our algorithm can accurately detect incidents, rather than predict them, and it can be adapted to various sites. The real-time capability of our system allows us to continuously transmit video and process a 2-minute segment in less than 1 minute and 20 seconds, providing detection results in real time. Throughout our project, we integrated both hardware and software components, including a smartphone app for controlling the drone and transmitting videos from the live deck. We also developed a user-friendly graphical user interface for alerts and ensured information storage for post-operations analysis. By using a thermal camera, we effectively avoid privacy concerns associated with visual imagery. Thank you very much for watching. Please feel free to contact us at the provided websites for any questions or potential cooperation opportunities.